Okay, so yesterday we were discussing the topic on this topic on continuous function. So today we are going to start with this topic only. Just let me know that if the screen is visible to you. Okay, just let me know if the screen is visible to you. Okay. Okay, that's good. Okay, yesterday we were discussing the properties of continuous functions, and while we were discussing those things, there were two theorems that I was discussing. One of the theorem was the extended mean value theorem, and the other theorem, sorry, not extended mean value theorem. There was a theorem called as extreme value theorem, and another theorem that we were discussing was intermediate value property, right? So these two were the things that we were discussing yesterday. Okay, now let us move ahead and see furthermore how to go about continuous functions. So yesterday I gave you a question also. Let us first see that whether we are able to solve that question or not. Okay. So yesterday I gave you one of the question, which was I think to find how many number of roots do you think will this x square equal to cosine x will have. Okay. So let us solve this particular problem at first. So what I'll do, I'll consider a function f of x given by x square minus of cosine of x. Okay. So I'll consider this as my function. Okay. Is that fine? Now you, if I just I try to find what would be f0. So f0 would be 0 minus cos 0, and cos 0 is 1. So this is minus 1, obviously less than 0. And further, if I want to find what would be f of minus pi by 2, so f of minus pi by 2 will be simply pi square by 4. Or even if I want to calculate f of pi by 2, it will be equals to what? It will be equals to pi square upon 4. Okay, so by the intermediate value property, there exists at least one real root in minus pi by 2 comma 0, and at least one real root in 0 comma pi by 2. So there would exist one real root in 0 minus pi by 2 comma 0. Why? Because you can see that at minus pi by 2 my function is having a positive sign. At exact 0 my function is having a negative sign, and at exact pi by 2 again my function is having a positive sign. So my function is changing sign from negative to positive. So by intermediate value property of continuous functions that we studied yesterday, there would exist at least one point in between 0 and pi by 2, and there would exist at least one point in between minus pi by 2 to 0 such that my function is 0. So there would exist at least one real root here and one real root here. And lately we are going to do some derivatives. Then we are going to study this thing in greater detail. But right now I will make a graph and let you know how many roots would be there. So another thing by which you can find the roots, or you can get an idea of roots, is to make a plot. So what I'll do, we know how x square is plotted. So x square is simply a parabolic graph, and we know how cos x is plotted. So your cos x is plotted this way. So this is how you're plotting cosine x, and this is how you're going to plot cosine x. So you can clearly see that there are two real roots here. So in fact, from graph, it is quite clear that there are exactly two real roots. So this is something that we know from graph, exactly two real roots. But from intermediate value property, you can only assert that there exists at least two real roots, from at least one real root in minus pi by 2 comma 0 and at least one real root in 0 comma pi by 2. From graph, it is evident that it is not at least, rather it is exactly two real roots here. So you'll get exactly two real roots. I hope it is clear. Okay, so should I move ahead? Okay, so now after having discussed all these things, let us do a few more questions, and let us first have a grasp on this continuity. Okay, let us have first grasp on our continuity thing. Okay, okay. So we've already seen that a function is said to be continuous. A function is said to be continuous if the limiting value of the function. So a function is said to be continuous if limit x tends to a f of x is equal to f of a. This is something that we already know. This is something that we already know. Okay. And another thing that there were two properties that I told you yesterday. One of the property was called as I did not give it a name. I'll call it extreme value theorem right now. And another property that we discussed yesterday was intermediate value property. The above question that we were discussing was a direct application of intermediate value property of continuous functions. Okay, is that clear? Now try to do this question which I'm giving you right now, and let's see if you're able to do it. Okay. So the first thing, a direct application intermediate value property is that every odd degree polynomial has at least one real root. Has at least one real root. So a direct application of intermediate value property is that every odd degree polynomial will have at least one real root. Okay, so let us see how to go about it. Okay, so let me write it in this fashion first. So let us consider that my polynomial px is some a naught x raised to power n plus a1 x raised to power n minus 1 plus a2 x raised to power n minus 2 and dash dash dash, and this will be an. Okay, now if I know that my n is odd, I know that my n is odd. I know that my n is odd. Now, if I want to find how my limiting value would be as x tends to infinity. So as x tends to infinity, let us assume, without loss of generality, let us assume that a naught is positive. Without loss of generality, let us assume that a naught is positive. Let us say that my a naught is positive. Now, if I want to find limit x tends to infinity, px, what it would be? It would go towards plus infinity. And how would limit x tends to minus infinity behave? Limit x tends to minus infinity, p of x would be equals to what? It will be equals to minus of infinity. So you can see that your function is changing sign for large values. Okay, so for I can write as x tends to infinity, your px is going towards infinity, and as x tends to minus infinity, your function is again going towards minus infinity. Or if you want to take some values also, you can take that. Let's say if I take x is equals to some 10 raised to power 12, let us say that I'm taking x is equal to 10 raised to the power minus 12. So clearly it is a very large value, and for this large value, these lower order degree terms I'm not going to consider. I'm just going to consider the higher order terms. So your p 10 raised to the power 12 can be almost approximated to a naught into 10 raised to the power 12 and this whole raised to the power n. Is that clear? And if I take another way in this towards minus infinity, if I want to take, so I'll take a very large number in negative. So this is x is equal to, I'm taking 10 raised to the power minus 12. So what will be p minus 10 raised to the power 12? It will be equals to a naught into minus 10 raised to the power 12 raised to the power n. And what is n? N is odd. So it will be equals to a naught minus 1 raised to the power n and 10 raised to the power 12 the whole power n. So obviously this is positive, no issues. But if n is odd, then this will become negative. So your p minus 10 raised to the power 12 would be negative, and your p 10 raised to the power 12 would be positive. So clearly your function is changing the sign. So therefore there exists, it implies that there exists at least one real root of this odd degree polynomial. There would exist at least one real root of this odd degree polynomial. So this is very certain. So now anytime if you are saying that how would your function behave, so if you have an odd degree polynomial, it will always have at least one real root. This you can see by theorification also. So I'll explain you in an easier sense also. Let us consider a cubic equation. Now what do you think? It can have roots. So it can have 3 real roots. Can it have all 3 real roots? Can it have 2 real roots and 1 complex root? Can it have 2 complex root and 1 real root? And can it have 3 complex root? So what is the possibility? So clearly you know that from theory of equation that complex root, if they exist, they always exist in pairs. Complex root, if they exist, they always exist in pair. Okay, so obviously there cannot be 3 complex roots and there cannot be 1 complex root. So these two cases I'm clearly driving off. I'm not writing them. Okay. Okay, and now if I want to know that what all possibilities are left, I can either have 3 real roots or I can have 2 complex and 1 real root. So for a cubic equation, at least 1 real root is guaranteed. Okay, so this is just for an example I'm saying. So whenever you have an odd degree polynomial, you clearly know that an odd degree polynomial will go towards infinity as x tends to infinity, and it will go towards minus infinity as x tends to minus infinity. So obviously, since it is a continuous function, it is going to cut somewhere, and it's not exactly at one point. It may cut at least at one point. So this is what our intermediate value property guarantees us. So whenever your function is a continuous function and it changes its sign from negative to positive, at least there will be one intersection on the x-axis, or at least 1 real root is guaranteed. Okay, is that clear? Okay, so I'll move ahead and give you a question, and then let's see how things are. Okay, so I'll give you a question right now. Okay, so again, this is, and please do remember this is an important topic. Like intermediate value property of continuous function is one important topic in your JEE exam. Okay, so we'll focus a lot on this. Try to show, I'm writing here question. Show that equation 1 minus x into cosine of x, 1 minus x into cosine of x is equal to sine of x has at least one solution in 0, 1. Has at least one solution in 0, 1. So you have to show that 1 minus x cosine x is equal to sine x has at least one real root at least one solution in 0, 1. Okay, so how to go about this particular problem? So what I'll do, I'll simply take my function as like whenever it comes to now questions, you will have to take some function. So let us consider the function. Let us consider a real valued function given by fx is equal to 1 minus x cosine x minus sin x. See what we, whenever it comes, see, and also look at the question itself. So question, you don't have any doubt, any hint given to you. One thing you know that this particular function cosine x is a continuous function. You know that sin x is a continuous function. Product of two continuous function is again a continuous function, because 1 minus x is a linear function. It is going to be a continuous function. So, and then difference and sum of two continuous function is again a continuous function. So by algebra of continuous function, fx is continuous function. So fx is a continuous function by algebra of continuous function. This is something that we have already studied. Okay, now you see this particular thing. So what I'll do, I'll try to find what is f of 0. First I'll try to find what is f of 0. So f of 0 would be equal to what? F of 0 would be equal to simply 1, which is positive. And then I will be trying to find what would be f1. So my f1 would be minus of sine 1. And you know that in the first quadrant, that is from 0 to pi by 2, your sign as such is positive. Your sign is positive. So obviously sine 1 would be also positive, because pi by 2 is around 1.54 or something. So 1.57 or something. Okay. So 3.14 divided by 2, what it will be? It will be around 1.5 some 2. Okay. 1. In fact, I should write 1.57 would be okay. So it is around 1.57. So obviously 1 would be some 1. This is angle in real terms. That is 1 would be somewhere contained in the first quadrant. In the first quadrant, sign is positive, and there is a negative sign here, so this will be negative. So one can. So it implies what? It implies there exists at least one x naught belongs to 0, 1, such that f of x naught is equal to what? 0. So there exists at least one real solution for this particular equation. Is that clear? Just let me know if something is not clear to you. Okay, now I'll move ahead. So there exists at least one x naught belongs to 0, 1 such that f of x naught is 0. What does it mean? It means that 1 minus x naught cos of x naught would be equal to what? It will be equal to sine of x naught for at least one x naught. Okay, this is what I want to say. Okay, now try to solve another question. So next question is, okay, so question is, let f be defined from 0, 1 to 0, 1. Let f be defined from 0, 1 to 0, 1. Then there exists x naught belongs to 0, 1 such that f of x naught is equal to x naught. Let f be defined from 0, 1 to 0, 1 be continuous. So I have to supply you something that it is a continuous function. Then there exists x naught belongs to 0, 1 such that f of x naught is equal to x naught. So these points where your function is equal, f of x naught is equal to x naught, these points are called as fixed points. I'm just giving you the vocabulary. So these points are called as fixed point. So what does it mean? It means that if your function is mapping on itself, that is f is defined from 0, 1 to 0, 1, and if it is a continuous function, then there would always exist some x naught belongs to 0, 1 such that f of x naught will be equal to x naught. So this is what we have to prove. Or if there is a function which is mapping from mapping onto itself, like mapping onto mapping to itself, that is f is defined from 0, 1 to 0, 1 here, and if it is a continuous function, then there will always exist a fixed point. these points where your f of x naught is equal to x naught. That is like, for example, if I want to say, does there exist a fixed point for cos x? Yes, there does exist, because see, if you want to make the graph of cos x and x, this is your x and this is your cosine of x. So clearly there is a point where x naught and cos of x naught are equal. Is that clear? So this particular point is called as the fixed point. This particular point is called as the fixed point. Okay, now we want to prove that if my function is continuous and it is defined from a domain to a codomain which are equivalent, then we want to find the existence of the fixed point. So let us see how. What is given to us? Given to us is that your function fx is a continuous function. Function fx is a continuous function, and let us define a function g of x which is equal to f of x minus x. So I'm defining a function on my own, that is f of x minus x. Fx is a continuous function, x is a continuous function. It implies what? It implies g of x is also a continuous function. It implies g of x is also a continuous function. Now if I want to find what would be g of 0, see, one thing is clear, that for all x, I'm writing here, for all x belongs to 0, 1, my f of x will always lie between 0 and 1 only, because see, my codomain is 0, closed interval 0, 1. So your range will be a range, after all, is a subset of is a subset of codomain only, no? So after all, I can write that my f of x will be between this only, that is, it can only lie between 0 and 1. Is that clear? Okay, now you see, because function is defined from 0, 1 to 0, 1, this is your codomain. I'm saying that range of function in any way would be lying between 0 to 1 only, right? So now try to find what is g of 0. So g of 0 would be f of 0 minus 0, right? And what would be f of 0? After all, for all x belongs to 0, 1, your f of x will lie between 0 and 1. So it implies that my g of 0, which is equal to f of 0, will either be greater than 0 or f of 0 equal to 0. दो पॉसिबिलिटी होंगी यहाँ पे, या तो ये होगा या ये होगा. Okay, now I'm writing it here itself. If, now for this case I'm writing, if f of 0 is equal to 0, then there is nothing to prove. Then there is nothing to prove. Why there is nothing to prove? Because if f of 0 happens to be 0 only, then you've got your x naught, isn't it? Then your x naught would be 0. This is what it was asked, that if there is a continuous function defined from 0, 1 to 0, 1, does there exist some x naught such that f of x naught equal to x naught? So your answer is yes, there does exist x naught equal to 0. However, here x naught was to be had to be an interior point. Here x naught had to be an interior point. If you can see here, that x naught should lie between 0, 1. Okay, so this case in general does not qualify this problem statement. Although if I would have made it closed interval, then you have found one x naught. Fine. See, what I want to say, that according to the given condition that I've written here, that let us assume another function. So g of x is another function which is f of x minus x. Now if I'm trying to find g of 0, it will be equal to what? F of 0. And f of 0 would lie between 0 and 1 only. So one case would be, if f of 0 is equal to 0, then there is nothing to prove, because then your x naught is equal to 0 only. So this is what we had to prove. But this is a trivial case. This is a trivial case. So we'll not focus on this particular point. We'll focus on this particular point. So if this is the case, this is fine. It implies what? It implies your g of 0 would be greater than 0. Either g of 0 would be equal to 0. Either g of 0 equal to 0, because it may be possible that f of 0 equal to 0. Or if f of 0 is not equal to 0, then what will happen? F of 0 will lie between 0 and 1 only. That I can write that f of 0 would be greater than 0. Is that clear? Now let us try to find what would be g of 1. Now g of 1 would be what? It would be equal to what? It would be equal to f of 1 minus 1. Okay, now I already know that my f of x lies between 0 and 1. So I can here also write that my f of 1 will always lie between 0 and 1 only. This is what it is, because f of x lies between 0 and 1 for all x belongs to 0 comma 1. So f of 1 will also lie between 0 and 1. So if your f of 1 is equal to 1, so I'm writing here there are two cases again. If f of 1 is equal to 1, then again there is nothing to prove. Why there is nothing to prove? Because you've got your x naught. You've got your x naught, and that x naught is equal to 1. But if this is not the case, if these are not the case, that is if f of 0 is not equal to 0 and if f of 1 is not equal to 1, then what will happen? So if f of 0 equal to 0, then it is fine. Then you have found your point. X naught equal to 0 would be such point. If f of 1 is equal to 1, again there is nothing to prove, because then your x naught has become 1. But if these two are not the cases, then what will happen? Then I will write that my g of 1 would be negative. Why it would be negative? Because my f of 1 lies between 0 and 1. Since my f of 1 lies between 0 and 1, if I subtract minus 1 from f of 1, your g of 1 would become negative. Is that clear? Now, g of 0 is positive, g of 1 is negative. What does it imply? It implies there exists at least one x naught belongs to open interval 0 comma 1 such that g of x naught would be what? Equals to 0. And if g of x naught is equal to 0, that implies your f of x naught minus x naught is 0. That implies your f of x naught should be equals to what? X naught. Is that clear or not clear? So I slightly modified the question in order to accommodate these two cases also. However, these two cases are like if f of 0 equal to 0, then there is nothing to prove. Okay, so therefore it does not involve intermediate value property. Here it involves intermediate value property. Is that clear? So always remember, whenever you are given in question, only continuity as a condition. So there can be two possible ways of asking it, or probably at your level, this intermediate value property will be more useful thing to be asked in examination, as far as I can think. Is that clear? I hope it is clear. Okay. Now what I'll do, I'll give you a few more questions so that let us see how much grip you have in this particular topic. And always remember, this is one topic which is really going to be asked in your examination time and again. So you don't have to leave this topic anyway. Okay, just give me a minute. I will give you a few more questions. Okay, so just try to solve this question. Okay, show that polynomial x raised to power 4 plus 6x cube minus 8 has at least two real roots. So we have to show that x ki power 4 plus 6x cube minus 8 has at least two real roots. I'm giving you a minute to think over it, and then I will solve. Don't worry. Okay, so I'll solve it for you. So for what I'll do, I'll try to find some values. Okay, so see, because I have defined it for bounded theorems, bounded intervals, so I'll use bounded things also. But see, one thing is for sure, that if I write my f of x is equal to simply x cube power 4 plus 6x cube minus 8, you can clearly see that as x tends to minus infinity, your f of x is tending to infinity. And if x tends to infinity, again my f of x is tending to infinity. Is that clear? So for sufficiently large values, negative values, for sufficiently large negative values of x, f of x is negative. And for sufficiently large positive values, positive values of x, f of x is positive. Okay, so for sufficiently large negative values, your f of x would be negative, and for sufficiently large values, f of x would be positive. Rather, if you can play with, I'll also play with some values also, but right now, if you're quite satisfied with me, satisfied with this argument, kindly let me know. Okay, and also see what will be the value of f of 0. So clearly, f of 0 is minus 8, which is negative. Okay, so minus 8 is negative. So clearly, as x tends to minus infinity, your function is here is positive. As x tends to infinity, again your function is positive here. And at exact x equal to 0, your function is negative. So your function changes its sign from positive to negative. Again, your function changes sign from negative to positive. So at least one real root is guaranteed here. And here also at least one real root is guaranteed. So in totality, I can say that my function, which is x cube power 4 plus 6x cube minus 8, will have at least 2 real roots. So it implies what? It implies x cube power 4 plus 6x cube minus 8 will have at least 2 real roots. In fact, you can remember this as a theorem also. So for example, if I want to write my polynomial a0 x cube power n plus a1 x cube power n minus 1 plus a2 x cube power n minus 2 dash dash dash, and if you have an and n is or even here, if n is even such that a0 and an, if their product is negative, then the above polynomial will have at least 2 real roots. There are two conditions that you should remember. First, that here n is even, I am writing, and secondly, the product of a0 and an must be negative. So here you can see the product of a0 was 1 and an is minus 8 here. So the product is negative, then it will always have at least 2 real roots. Okay, you want to prove it, you can prove it also. So in order to prove it, what I'll do, I'll take the highest power component. So if I want to find what is my limit x tends, let us write it as p of x. Let us find how would x tends to infinity px behave, and let us assume that your a0 is positive. So if your a0 is positive, according to the condition, your an must be negative. And you can take the other case also, but right now I'm just taking this case without loss of generality. So without loss of generality, I'm assuming that my a0 is positive, and according to the condition, if a0 is positive, then an would be negative. So how would limit x tends to infinity px would be, because a0 is positive and n is even, so this will go towards infinity. And limit x tends to minus infinity, if you want to evaluate, again it will go towards plus infinity only. But how would your p0, what would be your p0? P0 would be 0 0 0 0, and it will be equal to what? An, and an is what? Negative. So clearly function is changing its sign from 0 to infinity, and function is also changing its sign from minus infinity to 0. So there would exist at least 2 real roots. There exist at least 2 real roots. there exists at least two. I hope it is clear to you. Kindly let me know. Meanwhile, I'll write another question for you. Okay, so another question that follows. Okay, good. So, okay, so that is good that you're getting all these things, because these are slightly difficult topics. These are considered as slightly difficult topics by your. Okay, now try to do this. I think now you'll be able to understand. Okay, now I'm asking you another question. You have to find me. I'll write show that there exist at least one positive real solution of the equation modulus of x raised to power 31 plus x raised to power 8 plus 20 is equal to x raised to power 32. Show that there exists at least one positive real root of modulus of x raised to power 31 plus x raised to power 8 plus 20. So how to approach such problem? So again, in this problem also you can see that only this is given. So you know that this is a polynomial function. A polynomial function is a continuous function. No other hint is given to you. So what I'll do, I'll consider one function. So I'll consider f of x equal to x raised to power 31 plus x raised to power 8 plus 20. It's all fine. Modulus is fine. I will divide it by x raised to power 32 and minus 1. So what I've done, I've divided it and then I've taken this particular thing from here. So this will be it. Now you see, as x tends to infinity, see here the power is 31. So highest power is 31 here, and highest power here x raised to power 32. So if I want to find limit x tends to infinity, so as x tends to infinity, when you are taking large positive number, only the highest power dominate. So this highest power would be x raised to power 31. There is no need of taking modulus because this is positive only, because if x is very largely positive, then this will be positive. The modulus value of a positive number is again a positive number, so this is x raised to power 30. It will be simply 0 minus 1. This will be minus 1. This is negative. Okay. And if you want to find f of 0, what would be f of 0? F of 0 you cannot place because here you have divided it, right? You have divided it. So if you want to take you take some value, let's say some positive value. So what I'll do, rather I'll do this. So I'll take 0 plus. That is 0 plus means just close to 0 but towards the right hand side. So towards right hand side, if you want to find the value, it will be limit h tends to 0, and it is simply h raised to power 31 plus h raised to power 8 and then 20 mod minus 1 is here and then divided by h raised to power 32. Okay, and if you take like if you want to take if you can clearly see what I'll do. Okay, now here you see this is sufficiently small. H raised to power 32 is sufficiently small. Okay, this is fine. As h tends to 0, this will go towards 0. This will also go towards 0. So this is equivalent to writing limit h tends to 0 20 upon h ki power 32 minus 1. So you will say that here you have taken tends to 0 and here you have not considered it. Understand the fact that I'm adding something to 20. So if I'm adding very infinitesimal small amount to 20, I'll just approximate and I'll say no, there's no need of adding these two h terms. This is almost close to 0. So I'll simply write 20. And this 20 divided by h ki power 32, and here h is tending to 0. So this will go towards infinity. So I can understand closer to 0, my function is extremely positive. Closer to 0, my function is extremely positive. And as h x tends to infinity, my function is negative. Okay, is tending towards -1 and it is negative. So it implies there exists at least one x naught. So there exists at least one x naught belongs to what? It belongs to 0 comma infinity, such that f of x naught is 0. And if f of x naught is 0, what does it imply? It implies there exists at least one x naught such that x naught raised to power 31 plus x naught raised to power 8 plus 20 mod is equal to x naught raised to power 32. So simply if it is equal to 0, then we'll do all these things. So there exists at least one real root for this particular equation. Is that clear or not clear? Just let me know. Is that clear or not? I think it is clear. If you have any doubt, kindly let me know. Okay, chalo ji. So a couple of questions and then we'll finish this session. So I hope in this session you are going to get a good amount of exposure to this intermediate value property. And again, I'm reiterating, this is an important topic, quite important topic. Okay, and one of the things that you should understand is how to create some functions, how to create some functions. That is very important. So let f be defined from, this is your last question, try to do this, and then we'll continue from this topic tomorrow. Continue on this topic tomorrow also. So let fr2r be a continuous function. Let fr2r be a continuous function. Where that question was, such that f of x plus 2 pi is equal to f of x. Okay, for all x belongs to R. For all x belongs to R. Show that there exists some x naught belongs to R such that f of x naught plus pi is equals to f of x naught. Okay, so don't worry, I'll do it for you. So according to the question, always remember what is asked in the question. So let us consider a function g defined from 0 comma pi to r such that g of x is equals to f of x plus pi minus f of x, sorry. Okay, so this is the case. This is what I have taken as a function. Fx is continuous, so f of x plus pi would be continuous, so g of x would be continuous because it is sum and difference of two continuous function is always a continuous function. So I don't think it needs an explanation. Now what would be g0? So g0 would be simply f pi minus f0. So I'm writing the trivial case here. If g0 equal to 0, if g0 equal to 0, then there is nothing to prove. Why there is nothing to prove? Because if g0 equal to 0, then f pi would be equals to what? f0. And if f pi is equal to 0, f pi is equal to f0, then it is simply satisfying this equation with x not equal to 0. So then there is nothing to prove. There is already a solution to it. Fine. But if it is not the case, so here I'm writing if g0 is not 0, then it will be some value. f5 minus f0 would be some value. It will not be 0 in that case. Okay. So I'm not considering the case g0 equal to 0. If g0 equal to 0, then there is nothing to prove, because if g0 equal to 0, then f pi would be equals to 0. And if f pi is equal to 0, then obviously it is satisfying this expression with x equal to 0. So I don't need, it needs an explanation. If, what about g pi? What about g pi? Okay, so your g pi would be simply, if I see my expression, okay, it will be simply f of 2 pi minus f of pi. Is that clear? Is that clear? I mean, is that clear? Uh, just let me check if that's everybody's there or not. So is that clear or not? Just let me know so that I'll move forward then. And again, I'm writing that if g pi is equal to 0, again there is nothing to prove. Why there is nothing to prove? Because why there is nothing to prove? Because if g pi is equal to 0, then f of 2 pi has come out to be equal to f of pi. Then clearly I know that here this particular expression is true if I write x equal to pi. So obviously this satisfies this equation, f of x plus pi is equal to f of x with x equal to pi. So then there is nothing to prove. Here I know that x naught value would be pi. But if that is not the case, if g pi is not equal to 0, then what? So now just focus the attention not on these two cases but on these cases. So if g0 is not equal to 0, then obviously this will be some non-zero term, and when it is non-zero, either it can be positive or negative. Either it can be positive or negative. Now just pay attention to this term, f of 2 pi. Just pay attention to this term. It is given that f of x plus 2 pi is equal to f of x. Now if I write x equal to 0, what it is? It is like writing f of 2 pi is equal to f of 0. Yes or no? Okay. So if I write f of x plus 2 pi is given to be equal to f of x, then if I write x equal to 0, then f of 2 pi is equal to f of 0. And if this is the case, I can write that my g pi would be simply equal to f of 0 minus f of pi. So if this is positive, if g0 is positive, then g pi would be negative. And if g0 is negative, then g pi would be positive. You can clearly see that f pi minus f0 is written here, and g pi is f0 minus f pi. So clearly, if these two terms are non-zero, clearly if g0 and g pi are non-zero, then they will bear contrary sign. They will bear contrary sign. That is, if g of 0 is positive, then g pi would be negative, and if g0 is negative, then g pi would be positive. You can see f pi minus f0, and it is f0 minus f pi. It implies what? There will always exist at least one x naught belongs to 0 comma pi such that g of x naught would be 0. And if g of x naught is 0, what does it imply? It implies f of x naught plus pi would be equals to what? It would be equals to f of x naught. I hope it is clear till now. So if that's clear, I intend to meet you tomorrow and at the same time almost. And probably for a few days, because of my workload, I may not be able to teach you for long hours, but lately we are going to pick up the tempo. So this sums up our class on properties of continuous function, and this is mostly to do with intermediate value property. Okay, so we've done today quite many questions, and I'll do tomorrow also quite many questions on intermediate value property only.